Hey, it's Mr. K. Let's do a little bit of AP Physics 2 Thermodynamics, and we're looking at a PV graph. And so down here we have the pressure in atmospheres. We are going to have the volume in meters cubed. And so we have this process. We go from A to B to C, and let's just go ahead and start talking about what is going on in this process and the different processes that are going on here. So from A to B is a constant volume process. We call it isochoric. So from A to B, we're going to say this is an isochoric process, or isovolumetric would be another one, but volumetric's a little bit long to write, so I'm going to write isochoric. And what happens in isochores is that we have a constant volume, so as we increase the pressure, the temperature should rise. Okay, so you're going to get hotter as this pressure, or you get hotter so the pressure goes up, or you have the pressure going up because you're getting hotter. That's just either way. All right, from B to C, this is going to be an isothermal curve. So isotherm, and remember this word, the beginning iso, the prefix is the same, or we're going to keep it constant. So isotherm, or isothermal. That just means the temperature is going to be held constant. And so here you can see that nice one-to-one kind of curve, or 1 over x kind of curve for the isotherm. There is another process called an adiabatic, where it's going to look a lot like this, but it's going to be a little bit steeper. And that one is going to be a constant heat process, where no heat is added or removed from the system, but you could have work done and temperature change. C to A, we are going to go through a constant pressure process. So this is going to be an isobaric process. And in an isobaric process, the pressure remains the same. One particular difference between these three processes is that in some of them work is done, some of them heat is added, some of them work could be done negatively, and heat could be removed. So we need to look at that. So work in a thermodynamic system is going to be the pressure times the change in volume. So if there is no change in volume, then there would be no work done. And so for one of these processes, this one right here, there is no change in volume, the isochore. So there's no work done for it. Another thing that we can look at is the change in internal energy, and that's going to be 3/2 nRT delta T. Or we can talk about the actual internal energy, which is going to just be 3/2 times T, the Kelvin temperature that it is currently at. Change will be the change in Kelvin temperature. So without a change in temperature, there would be no change in internal energy. And lastly, we can consider the law of conservation of energy, which would say that the change in total energy of our system, E or delta U, is equal to the amount of work done plus the Q that's going to be added or removed. So this could be plus or minus for either one. So let's go ahead and start talking about A to B. A to B, we have the system going from some point where it's 400 Kelvin up to another point of B at constant volume. What that's going to say to us is that, hey, the temperature should rise, because if we look at the ideal gas law, let's just add another equation up here. Ideal gas law is PV equals nRT. All right, and the combined gas law, which is just assuming that our moles and our ideal gas constant stays the same, would say P1 V1 over T1 is equal to P2 V2 over T2. So we just move that T over and set it equal to itself at a different case. So from A to B, let's just check out what can apply here. We are starting off with a certain amount of temperature, 400 Kelvin. If you notice that the temperature on the right side is defined by the product of P and V, so as we go more away from our origin, our temperature would be rising, and so the product of those two things would result in a temperature. That's why at B and C the temperature would be the same, because the product of these values and the product of these values would be the exact same. So, isochore, once again, A to B, work is 0. 0 work is done. And we get hotter. So our temperature does go up. So if our work is 0 and our temperature goes up, then that means that our Q should be added. All right, we need to add in some amount of heat here. All right, and if our temperature change is positive, that results in a change in energy that is also positive. So we gain energy in this process from A to B. From B to C, that means that there is no temperature change, which would result in no change in internal energy. But work is definitely done. So we need to talk about work being done by the system or on the system. And for right now, I'm going to talk about work done by the system. So this system is expanding. You can see the volume increasing. And so when that system expands, it pushes out on the surrounding air. And it's going to take some energy to do that. So the system should be cooling down. Well, the isotherm is going to be a little bit different. So here, the work, I'm going to say the work done is positive. And it's going to be work done by the system. And so if the work is done by the system, actually, we'll go ahead and make that negative. Because we're going to say, hey, work is done by the system, and that means that we're going to have energy loss. All right, so the work is done by the system, we're going to push out, and we're going to have energy lost by that system. So we'll just make that negative here. It really depends on your perspective and how you talk about it. But here, we'll call it negative. All right, what else is happening with this isothermal curve? The isothermal curve is a change of temperature of nothing. So if a change of temperature of nothing, that means the change in internal energy total is nothing. But hey, we were supposed to lose energy because this system is doing work. This balloon is expanding, and this air is expanding, and so we need to lose energy. It should get colder, but it doesn't. So if it doesn't get colder, that means that we are going to have Q is going to be added. Okay, just like before. But here, the reason why is because we need to keep this temperature the same. It would want to cool off as it expanded, but we want to keep that temperature the same. So work done by the system is going to be negative. We're going to lose energy because of that. The change in temperature is going to be 0. No change in internal energy. Q needs to be added because we should be cooling off if our system's doing work. Lastly, we're going to have this C to A step. It's going to be isobaric. The temperature is going to change. We should have a colder temperature now. And so this is going to be a compression, so work is going to be done on the system. So work being done on the system, we're going to say that we have positive work, so we're going to get energy. So energy is going to be gained in this scenario. If energy is gained, well, due to kinetic theory, that means that we should be getting hotter, but we're not. Our product of pressure and volume is actually getting lower, okay, as we go here. So that means that our temperature change is a negative temperature change, which is going to result in a change in internal energy of lesser. But we're having work done on it. This doesn't make any sense. So if we are having work done on it, it should get hotter, but it doesn't. It actually gets colder. And the way that we solve that is that Q would have to be removed from the system. Okay, so in process A to B, no work is being done, but we are getting hotter, so we have energy added, heat added. From B to C, work is being done. We should be cooling off, but we don't, so we got to add heat in to counter that effect. And from C to A, we should be cooling off because we're closer to the origin. Remember that product of PV? That's going to result in that T value. So if that starts to get lower, our temperature should get lower. But if it doesn't, that means we got to, and so if it doesn't, it's supposed to get colder, but we have work being done on this system. And so we got to take that heat out in order for it to get colder. All right, so this work is being done to compress it. It should get hotter by compressing it, but it apparently doesn't in this case, so we got to remove heat. All right, so the last thing that we can look at is the temperature at each of these different spots and possibly the volume. I think the question that I was looking at for this one, it wanted to find the volume at point C. And so in order to find the volume at point C, we would probably need to know the temperature at B or C, which would be the same temperature. And let's see if we can solve some combined gas law for that. So for A, at point A, we know the pressure at point A is 1 atmosphere. And 1 atmosphere is 101,300 pascals. And I don't think we need to convert it here. Sometimes we will have to, but sometimes we won't. The conversion would just be a multiplication, and if we use combined gas law, it's just multiplying the same thing on both sides. So really, we wouldn't have to here. But looking at this, let's go ahead and try to find the temperature at point C or A, so that we can find the volume there, because we know the pressure. So if we know pressure, we would need to know temperature to find the volume. Can't find it directly at C yet, but we could find it at B. So let's say that we have the pressure at A, the volume at A, and the temperature at A should be equal to the pressure at B, the volume at B, and the temperature at B. Now, as we notice, for A to B, our volume stays the same, so that would cancel out. And so we just need to talk about the pressures. So the pressure, we go from 1 atmosphere and we turn it into 5 atmospheres. And the temperature is at 400 Kelvin. And so if we look at the value for that, we would have to multiply our temperature by 5 times. And that's going to be 2,000. Right? So 5 times 4 is going to be 20. It's going to be 2 zeros on that. So that should be 2,000 to be the same ratio. So the temperature at the B part is going to be 2,000. Just to double check, because sometimes our math is screwy. 5 times 400, 2,000. So we have 2,000 up here. Kelvin, that means that it's going to be 2,000 Kelvin down here due to isothermal. And now we can actually find the volume here. And so let's just compare these 2 points again. I've got the pressure at A, which is 1 atmosphere, the volume at A, which is 0.001. Move that up a little bit. And the temperature at A, which is going to be 400 Kelvin, and that's going to be equal to the pressure at A, or C, which is going to be 1. That'll cancel out. The volume at C, that's what we want, divided by 2,000. So we're going to have 0.001 divided by 400 multiplied by 2,000. And that's going to give us 0.005. So V at C is 0.005, and that's going to be meters cubed. Okay, so that is a simple PV diagram. Looking for energy changes due to work, due to heat added or removed, and using the ideal gas law and the combined gas law to really find out different parts of this graph.